Good evening, chaps. This spicy little numbers from the BARKER past paper we've been doing. It's question 13 from the 2012 Extension 1 Semester 1 paper. And this little darling's all to do with the quotient rule. And as you can see, it's a real long one. It's a bloody novel. So we're only going to do the first three parts. So just up to the third part in this video, just to keep things short. And also because I want to hit the bed pretty soon. So the first question is, show that f of x, which is this function here, and it's a bit of an unorthodox looking thing, e to the x over 3 plus e to the x, in the range of 0 is less than y, which is less than 1. So it just means, don't too much worry about what that means now, because we'll see that this function only exists in the range of, so we're going to have, the y values are going to stem, maybe it's easier if we write this, 0 is less than y, which is less than 1. And that's just giving you a bit of a hint as to what this function's doing. But the first part we've got to do is show that it has no stationary points. And hopefully you've seen, say you've got this graph, like any old graph, just say this one here. A stationary point is a line where the tangent is flat on that curve. So its gradient is 0. So we've got to we've got to show that this graph doesn't have any of those. So the graph's going to look something like, this or something where, the gradient is probably flat there. Maybe that's a bad one. Maybe something like that. That the gradient isn't flat there at all. So we've got to prove that it's something like this. So the quotient rule, if you haven't seen it before, is something used when you've got a quotient, and a quotient just means a fraction. So say we've got a function of say u of x. In this case, u of x is just this e to the x on top, and over here we've got on the bottom we've got some function which I'm going to call v of x on the bottom, and v of x in this case would be 3 plus e to the x. So when you've got a function that's a quotient like this or a fraction. So what we're going to do is this is the function that we've been given, and we're going to differentiate it to find the first derivative of the gradient function. And so I've written here, this is the quotient rule. So if v is the one on the bottom and use the one on the top, then the derivative, now people remember this in different ways. I remember it as this big mouthful, v u dash minus v dash u all over v squared. So that's one way of remembering it. I remember another maths class remembered it as the bottom times the derivative of the top minus the derivative of the bottom times the top all over the bottom squared, and that was just a mouthful for me. Not a chance I could read that. So I've just remembered it in this form, and this quotient rule is definitely something worth committing to memory. So I've just written down things. So the u in this case is the thing on top, e to the x. So its first derivative u dash is e to the x because the derivative of e to the x is just e to the x. The bottom you can see v represents the bottom over here, and the bottom is 3 plus e to the x. And the first derivative of the bottom, this 3, when we differentiate 3, it's just a constant, so we get 0. And then when we differentiate e to the x, we just get left with this e to the x again. Beautiful. So what we can do is just plug these into the quotient rule. So I've just rewritten the quotient rule here. So v is, what was v? V was 3 plus e to the x. Too easy. U dash, what was that little girl? That was u dash was e to the x. Too easy. Minus, now v dash. So we've got e to the x just here. E to the x is v dash. Times u. So what is u? U is e to the x. Too easy. All over. Now this is a huge trap for young players, folks. I always used to forget this squared here. Always. So v, which is the bottom. In this case it's 3 plus e to the x. So we've got to square that. So 3 plus e to the x all squared. Remember that squared. I used to always forget it. So now what we're going to do is, don't mind what I've got going on down here. Sorry about that, kids. So we're just going to expand. So 3 times e to the x will be 3 e to the x plus e. So we're going to have e to the x times e to the x. That's going to be e to the 2x. Beautiful. Minus, and this is going to be e to the x times e to the x. So it's going to be e to the 2x. So those e to the 2x minus e to the 2x, that's going to cancel. And we're just going to get left with this plus 3, what are we going to get? E to the x squared on the bottom. Beautiful. So we've just got left with, I'll just rewrite it over here. So f dash of x equals, so we had this 3e to the x on the top, 3e to the x on the top, and this 3 plus e to the x squared. Beautiful. So this is the first derivative. This is the gradient function of this function here that we've been given. And hopefully you've seen before that stationary points, or the points where the gradient is flat, occur when f dashed of x equals 0. Because that means, so this is the gradient function. So when we put 0 in here, we're saying, okay, when the gradient is 0 and we solve for x, we're saying what values of x is the gradient flat? Beautiful. So if I'm going to pop in 0, so when f dash of x equals 0, then 0 equals 3e to the x, all over 3 plus e to the x squared. Beautiful. And the only way this can hold is if this numerator is 0, because if the denominator is 0, I mean, that doesn't do anything. It just means we're dividing by 0 and the world explodes. So that's no good. So the only way this can occur is if 3e to the x equals 0. All right? But we know that the graph of 3e to the x looks something like this. So when x equals 0, we pop it in here, we're just going to get 1. So, and that we're going to times it by 3, so we're going to get 3. And we know it's this exponential function that looks something like this. Right, so this is the graph of y equals 3e to the x. And we're saying, where does that cross 0? Well, it never does it. It asymptotes at 0. So this never holds true just by looking at this graph of y equals 3e to the x. It never crosses the x-axis, or so also called the abscissa, but you don't need to know that. It never crosses the point where y equals 0. So we can write, therefore, no solution. Beautiful. So if there's no solution to when the first derivative equals 0, then there is therefore no stationary points. Beautiful. So I'd probably say that. I don't really have much room, but I'd probably say something like, and I don't want to bore you, I'd say something like, because the first derivative has no solutions when f dashed of x equals 0, therefore there are no stationary points. Beautiful. So that's 2 marks in the bag. Thanks for coming. So now we're going to do this second part. So it says, given that the second derivative is this whole hunk of nonsense. Beautiful. So we don't have to prove it. We probably could if you were that way inclined, and we could differentiate this first derivative again to get the second one. But now we've given it. There's no way you're doing that because it just takes too much time. Find the coordinates of the point of inflection. You do not need to show a change of concavity. Beautiful. So I've just drawn down here. So a point of inflection you might have seen before is this point here, and I've just stolen this from Google. So you see here we're getting steeper and steeper and steeper as we're going down the hill. We're going, oh geez, like imagine you're a car going down here, right? And great little car, and you're going this way, and it's getting steeper and steeper and steeper. But here, when you're a car, is going down, it's getting flatter and flatter and flatter. So as you're going down, it's flattening out. So here you're getting steeper and here you're flattening out. Where did that change? It changed at this point of inflection. And point of inflections occur when the second derivative equals 0. So, i.e., when this thing here equals 0, this whole mess here, that's when we're going to have a point of inflection. And the only way that this second derivative can equal 0 is if this numerator equals 0. Because if this numerator equals 0, then this right-hand side will equal 0, and then beautiful. So let's write that. So point of inflections occur when, so we'll write 3e to the x, and what was the other part? 3 minus e to the x. Beautiful. 3 minus e to the x. So I'd say point of inflections occur when the second derivative equals 0, I dot e, so that means that is when this equals 0. Beautiful. So that means that 3e to the x could equal 0. So either this thing here could equal 0, or this thing here could equal 0. Because if this equals 0, then we're timesing that by this thing, and then 0 times this will be 0. But if this 3e to the x is 0, then we're timesing this thing here, and that's going to be 0 again. So this is one possible way that can happen. The other possible way is 3 minus e to the x equals 0. Cool. Now, we've just shown in the point above that this can't happen. No solution, because it was exactly that. We were trying to find where this 3e to the x could equal 0, and we showed in this graph that it never cuts the x-axis, so it never does equal 0. So that's why there's no solution here. However, if we go e to the x, and so we plus e to the x over the other side, so I've just added e to the x over here, so plus e to the x over here, and so that got rid of it here, and then I'll just swap those two around. Sorry about that, sorry if that was confusing. Now what we can do is we're going to try and solve for x. So let's use logarithms here. So log base e of x. Let's think about that. So what the definition of this, just by definition of a log, that means if we rewrite this in terms of the step above, we're going to get e to the x, which is what we've got here, equals 3. Beautiful. So what I've got here in orange and what I've got here in yellow are exactly equivalent statements. Beautiful. So that means x equals log of 3, natural log of 3. Beautiful. So at this point here, x equals log of 3, we're going to have one of these point of inflections. Beautiful. And the third question is, describe the behavior of f of x. So that's one mark we've just got there. Describe the behavior of f of x, which remember is this thing. Remember, but you've got to remember what function you're using for as x approaches infinity and as x approaches minus infinity. So to be honest, guys, the best way of doing this is just working out what, chuck in f of 100, and you're going to get something very, very close to 1. You're going to get like 0.999 or something. And then chuck in f of minus 100. So put minus 100 into these points, and you're going to get something very close to 0. Beautiful. So and that's just the easiest way to work out what's happening for very large and very negative values. So I'd say something. So and you can think about that. I mean, as x, you put x equals 100 in here, you're going to get a huge number on the top. E to 100 is a huge number, and then you're going to get that same thing on the bottom plus 3. So the numerator is going to be just smaller, like a tiny little bit smaller than the denominator. So it's going to be 3 less, but in terms of fractions, it's going to be just small. So it's going to be really close to 1. So that's where this comes from. So what I'd write is, after you've chucked into your calculator and you believe me, I'd just say something like, as x approaches infinity, x approaches, 1? Beautiful. And as x approaches minus infinity, no, what I should have written there, not x, we should have written f of x approaches 1. Beautiful. And as x approaches minus infinity, f of x approaches 0. Beautiful. So that's the 3 we're going to do in this question. Hope that was clear. So you can see why I've broken up to 3 already at 13 minutes. So I've broken that up into 2 parts. So we'll crack on with 4, 5, and 6 in the next video. See you guys.